Hello. Yeah, so I'll be talking about some kind of weird cryptography. People probably heard, about ZK and maybe MPC and FHE, and these are all cool. But I think we should pay more attention to lesser known primitives, and I think they can be useful. And yeah, so, limitation is the essence of creativity, right? Like, weird constraints breed novel solutions, and that's definitely been my experience working on Bitcoin stuff. And so, at least for us, right, a lot of the common types of approaches to solve problems are not feasible. We have to be creative and come up with, interesting or unusual approaches. And the literature of cryptography is very large. There's lots of protocols with lots of really weird properties that people who created them didn't really care whether they had applicability to the real world. So I think, I'll talk about an example basically of how we found protocols like that and have been able to use them to do real things. And then hopefully we can kickstart a virtuous feedback loop, like we had with ZK, right? The story of ZK is very theoretical, lots of research, but not practical. And then people wanted private money on the internet. And so somehow the threshold of people wanting something crossed what was feasible, and then it started to snowball from there. So I want to catalyze more of that. So yeah. So the problem we were working on is verifying Snarks on Bitcoin, which is not possible. In order to do that, people have lots of complicated solutions, and the one we use is called a conditional disclosure of secrets. So many people might not have heard of this, but it's actually pretty simple. And then we had to do a lot of work to make this practical. And one of the things that we did to do that was designated verifier Snarks. Another thing that not a lot of people have been thinking about, maybe, where you don't have just one person who can verify, or you have only one person who can verify a proof. And we can simplify things that way. So I'll talk about that, and then going forward, what more we can do. So witness encryption, functional encryption, obfuscation. These are all things that are kind of on the horizon of possibility that aren't really possible now. But I think if we pursue this weird cryptography path, we can maybe find a way to get there and get people interested in them, and yeah. So the reason we want to verify Snarks on Bitcoin, probably not that surprising. We can use them to verify anything, and so it sort of reduced the whole problem of smart contracts, or at least some parts of it, to a single primitive. And it's not possible, because Snark verifiers are too big. The restrictions of Bitcoin, on script size and stack usage, are too stringent to fit any kind of plausible Snark verifier. There are ways that we can do this, which is what we have worked on previously, called BitVM. It's a very complicated protocol. It's has optimistic elements. It requires writing a Snark verifier in Bitcoin script. Yeah, so. Can we do better with cryptography? So I think the useful way to think about these things is to first consider what you can do, and then sort of see if anything fits inside of the space. So what we can do on Bitcoin is we can require someone publish some secret information in order to spend some money, or to take some money. You can reveal a hash preimage. You could do an adapter signature. There's many ways to do this. We can also condition certain payments on knowing something. So you can only take this information, you can only spend this if you know the secret key. This is very, very basic stuff of transfers. We can also build multi-round games on chain. So Alice sends something to Bob, sends something back to Alice. This uses pre-signing. So this is an additional assumption that we make that people might not like, but without covenants, that's the best we can do right now. And it's acceptable from our perspective to build an optimistic protocol. So like a snark on Ethereum will simply not be valid if the proof doesn't verify. We need to relax that, which is part of how we get to this like weird cryptography stuff. So we allow like people to challenge the validity of a snark rather than having it checked by consensus. So given this stuff, we can kind of describe abstractly what a solution might look like if we had some magical cryptographic technique to do this. To like initiate a proof, like to make a claim, the prover puts some secrets on chain that encode the proof, right? They move some money, and in doing so, they have to put secrets on chain. Then, like, this is where the magic cryptography comes in. Like, if the proof is invalid, we want someone to be able to derive a different secret that's like, no, you lied. This is wrong. And if they have that secret, then they can use it to slash. So it's like, we're basically just using the blockchain for communication. The prover puts some secrets on chain that initiates the game, and we want to be able to derive a slashing secret if they're misbehaving. So how do we do that? It turns out there is exactly like this specific thing, conditional disclosure of secrets. There are ways you could do it more generically with more powerful cryptography, but this is sort of narrowly exactly what we're talking about. They're not even like that weird. They're maybe underappreciated, but the construction is pretty simple, at least in terms of these types of things. You can use garbled circuits, which people might have heard of from like MPC world. They're very well understood, simple protocol, or there's many variants, but you can sort of do it with any of them. And the kind of shift in perspective that, I mean, we're not the first people to do this, but that was required to like understand why this is interesting, is that usually people think about garbled circuits in terms of privacy. So like Alice and Bob are computing some function and they want to keep information secret from one another. But garbled circuits also provide authenticity. They allow you to like prove that you ran a computation on a particular input to get a certain output. They leak a secret as the result of executing the protocol. And that's what we want. We want the challenger to prevent like malicious challenging, to sort of implicitly prove that the original claim is false. So there's lots of different garbled circuit schemes, many different properties. Unfortunately, nothing like off the shelf was practical for our use case. We want to garble a Groth Verifier, which is very big, and so we had to do more work. So we kind of like found this piece that sort of works, but not quite. But it gets closer. Like before we had no idea what to do. So the Groth Verifier is like 10 billion gates, 10 billion binary gates, something like a 50 gigabyte garbling table. It's also not maliciously secure. So the person who sort of sets the whole game up could construct the table in such a way that even if you tried to slash, it would fail. So that's obviously not going to work. So the idea here that we're going with is to kind of, again, like relax what we're trying to do. And this is where the designated verifier snark comes in. So for technical reasons, Bitcoin requires a permissioned light client. The details of this aren't super important. It just means that like, in order to challenge like which is the canonical Bitcoin chain, you can't allow anybody to do that because it's vulnerable to these kinds of griefing attacks. So we're already assuming this. This is like another constraint that I didn't list before that we realized later was already part of the system. So because we already need permission challenging, the prover and the verifier are sort of both known ahead of time. And that's what allows us to use a designated verifier snark. Usually snarks can be verified by anybody. If we know who the verifier will be ahead of time, then we can use a simpler protocol. There's a much larger, I mean, certainly any like regular snark is also suitable, but we can use more efficient protocols. It turns out that after kind of hacking on it for a while, the circuit complexity is like 5,000 times smaller. So it goes from 50 gigabytes to maybe 10 megabytes. So this is sort of like the difference between practicality and not. I also contend that designated verifier snarks are more interesting and useful than people give them credit for. They, in many cases, they are actually what you want and are more efficient, but you know, you have to consider your use case. And actually, there are places where being designated verifier is like a desirable property, specifically in reputable identity attestations. So if you prove your identity to someone, you might not want them to be able to talk about what you proved to them. So if they're the only person who can verify your proof, then they can't do that. So anyway, something to think about. We don't really use that here. We're just using the efficiency of designated verifier. Okay, so what have we done? We want to verify snarks on Bitcoin. It's not possible directly. We have relaxed a ton of assumptions to make this work. Work with Bitcoin and be practical with garbled circuits. We allow sort of these on-chain games with pre-signing, so that's an additional assumption. We pre-share this garbling table, which not 50 gigabytes, but 10 megabytes is a lot to share ahead of time. And because of the specific use case that we're working in, it's fine to use designated verifiers. There's no degradation in the security of the scheme, just pure efficiency. And so in this model, we can find more obscure cryptographic tools to solve the problem. We can use conditional disclosure of secrets. We can instantiate it with relatively normal garbled circuit protocol. And we can use a designated verifier snark. All of this kind of comes together in a neat little package that's pretty efficient and better than the state of the art, I think. So what else can we do? That's the big example, but I think that pursuing this line of protocol design will yield potentially improvements in the primitives themselves. So we have interactivity, we have pre-computation, known parties, all of these things allow us to use cryptography to solve more problems, to simplify, right? That's what we did. And then hopefully this will initiate, as in ZK, the virtuous sort of research and development cycle, where we have this thing, we've done a bunch of stuff, it's crossed some threshold, we can use it, and then people will start improving upon it. And improving upon it will bring increasingly more complex things closer to practicality, and hopefully this will snowball. And some of these newer primitives that I'll mention might become possible. And so each of these subsequent cryptographic things is kind of going in the opposite direction. It's we introduce these assumptions to get closer to what's possible now, and then if we do more work, maybe we can then relax some of the relaxations and get better protocols. So the first thing I'll talk about briefly is witness encryption. So witness encryption is an encryption scheme where you can encrypt something to the solution to a puzzle. So if you can solve the puzzle, you can decrypt the result. This is pretty similar to the construction that we're using, except witness encryption is non-interactive. So in our scheme, somebody posts a proof on chain, and then you run a sort of garbled circuit to check it. Imagine if instead of a particular person posting it on chain, anyone could put it on chain. So it would sort of make anybody able to be an operator. That would be witness encryption. Witness encryption is not known to be possible, but maybe somebody will figure it out. Yeah, so instead of a particular person needing to handle the withdrawal, anybody could do it. They would just put a proof on chain, and you'd run the witness encryption, and if it worked, then they would get the money, just atomically one thing. This is sufficient to add programmability, or a lot of programmability to Bitcoin. Not everything, but it's quite a lot. So yeah, I mean, there are witness encryption schemes that are similar to what we're trying to do. There are witness encryption schemes that are very different, and I think I'd like to be able to work on this kind of thing and try and make it more practical. And I think just talking about this, raising awareness that these types of things, they're defined, we just don't quite know how to do them yet. So going further past witness encryption, we have functional encryption, where witness encryption, you provide the solution to a puzzle and you learn a secret. Functional encryption goes further and allows you to learn some function applied to the secret. So in the previous case, I said you post a snark and you learn a secret that lets you take some Bitcoin. Functional encryption might let you do something like you post the snark and then you receive a signed transaction. Like you don't receive the private key, it actually produces the whole thing for you. So you wouldn't leak the secret, you just like have an oracle that signs transactions for you. Yeah, it can transform the secret, right? It could start a signature or something like that. Another way of thinking about functional encryption is like FHE with public outputs. So people might have heard of like multi-party FHE, that type of stuff. Functional encryption is the way to solve that without trust assumptions. It's just a blob that takes some computation and produces a public output. FHE only produces encrypted outputs. You need some threshold of people to decrypt it for you. This is like extremely complicated. There's like many different types. They're not equivalent. But the big thing about functional encryption that's cool is you can use it to build obfuscation, which I will talk about briefly. Obfuscation is the ultimate form of cryptography. It is equivalent to like, I don't think literally everything, but most things. So I will describe black box obfuscation. It's not technically possible, but it's sort of the way to think about it. You can take a program and obfuscate it. So you can take the program and produce a blob. The only thing you can do with the blob is run it. You can't see its contents, you can't read the source code. If you put a secret key inside of the program, you cannot read it out. You can only run the program. So with this primitive, you can do all sorts of crazy stuff. You could have like a smart contract with private state, right, that nobody knows. It's just living inside of this blob. In some ways, it's like a cryptographic TE, if that means anything to people. This actually allows you to add smart contracts to Bitcoin. If we could do this, we could just get rid of everything and run everything inside of obfuscation. There are like, mostly, yeah. I think thinking of it like a computer that you just cannot peer inside of, and it can do anything. So anyway, can't do verifiable delete. That's the only thing it can't do, I think. So all of this is to say we should be open to exotic cryptography. If you relax your problems, you can maybe apply some interesting techniques to solve them. And if we all do that, we'll have more people looking at this stuff and people thinking about it, and maybe we'll find more applied people that can work with theoretical people that can bring these two sort of frontiers together and unlock these weird advanced cryptographic primitives. That would be really great to have. Do lots of cool stuff with it. Yep. Thanks.